Welcome to this third talk of the European Tensor Network. It's a great honor to introduce Philippe Corboz. It's not so difficult to introduce Philippe because Philippe is iPEPS and iPEPS is Philippe. So please, the stage is yours.
Okay, thanks a lot for the introduction. And also thanks a lot for the invitation to speak here as the third speaker. So that's a great honor. Thank you very much. And so the topic of today is going to be about the 2D Hubbard model. And of course, for those who were around 4 weeks ago, we had already a very nice talk on the 2D Hubbard model by Steve White. So he focused mostly on the DMRG results. And I would like to talk about today is about results obtained with iPEPS, right? So, which as you probably know is a 2D tensor network ansatz to represent 2D wave functions directly in the thermodynamic limit. Okay, so here's the plan of my talk. I will start by telling you about a work together with the Simons collaboration on the many electron problem. So as you see, that involved many people here. So Bo Jia Sheng, Jiamin Chung, Georg Ehlers, Ming-Po Qin, Reinhard Noack, Hao Shi, Steve White as well, Shi-Wai Zhang, and Garnet Chan. And the goal of this work was to focus on one particularly challenging point in the phase diagram of the Hubbard model. So U over T equals 8 and 1/8 doping. And then by pushing several methods to the current limits, the goal was then to really find out what is the ground state at this particularly challenging point. And what we found here was that it's a stripe state with a period of 8. So as shown in this picture here. Okay, so I will use this as a starting point to tell you about a more recent work, which is about an extended 2D Hubbard model. So together with an additional next nearest neighbor hopping term. And what we found here is that the preferred stripe period, so the ground state period, changes from period 8 to period 4. And period 4 in the end is also the typical stripe period, which is observed in the in experiments on the cuprates. Okay, so that's work done together with Boris Bonsun and Sang-Wo Chung from our group. So this is going to be the main part of my talk, but then I will also tell you about a related recent topic, namely generalizations to several species of fermions, so SUN Hubbard models. And in this context here, we have been looking at the SU3 Hubbard model on the honeycomb lattice, where we found 2 different competing states and a phase transition between them as a function of U over T. And then in the very end, I would also briefly like to mention some of the recent advances with iPEPS on the method side. So to do calculations beyond ground states, namely finite temperature simulations and the computation of excitations. Okay, so I guess all of you have seen the Hubbard model before, which can really be seen as the most basic model of strongly correlated electrons. And it's in its most basic form, it just has a nearest neighbor hopping term, so with spin up and spin down, and then 2 electrons on the same side repel each other with a repulsion strength U, right? And despite an enormous effort in trying to solve the 2D Hubbard model for 4 or 5 decades, there's still no full consensus about its phase diagram and also about the question whether this is really the relevant model to understand hybrid high TC superconductivity of the cuprates. And of course, one of the main reasons why it has been such a big challenge is that you can't use just conventional quantum Monte Carlo because of the negative sign problem. But still, there has been substantial progress in the past decade in studying the 2D Hubbard model with a variety of different numerical approaches. So you see here, it's a long list of different approaches, and in the end, all of those have their own advantages and disadvantages. So unfortunately, there's still no magic black box method which can just solve everything. But as all these methods become more and more accurate, the hope in the end is that at some point they will give conclusive and consistent results with respect to each other. And this in the end was our motivation to do such a joint study where we tried to nail down the ground state really at one point in the phase diagram. Now there have been many predictions for the ground state of the 2D Hubbard model And here we focus on the strongly correlated regime, so U over T around 8 and 1/8 doping. And there have also been many predictions for the TJ model, which is the effective model of the Hubbard model, right? So essentially, if you go to half filling, so at 0 doping, then the ground state is well understood. It's just the Heisenberg limit in the end. So we have a state with antiferromagnetic long-range order. But the question is then really what happens once you start doping the system with holes? What do these holes do, and what type of ground state is arising here? And now the two most common predictions here, on the one hand, a uniform D-wave superconducting state, so where we have a uniform hole density, and on the other hand, a stripe state, so where these holes then form domain walls, which separate antiferromagnetic regions in between, so where the spin and charge density is modulated. Now, there's a long history on the theory of stripes that I'm not going into. So initially, stripes were found to be insulating, but later on, people also found stripes that coexist with superconductivity, so where all spin, charge, and superconducting orders are intertwined. Now, from a numerics perspective, the situation was as follows if you go a few years back. Namely, there have been many works supporting this uniform D-wave state as the ground state, whereas in other many works, they found stripe state as the ground state, and then yet in other works, they find both states, but then extremely close in energy, right? So for a very long time, it has really been an open question, which of these two candidates is really the true ground state here. And in the end, the goal of our collaboration in the end was to nail this down for this point in the phase diagram using a combination of methods. And as I already mentioned, what we found here is that the ground state is a stripe state. Okay, so I will show you in detail the iPEPS results. But before I get there, let me just briefly give a very quick introduction to iPEPS. So I guess for this audience here, I don't really need to tell you what a tensor network ansatz is, right? So we use a tensor network ansatz as an efficient representation of ground states of local Hamiltonians, as for example, shown here, a matrix product state where we can control the accuracy by the bond dimension D. And the reason why we can use such a representation is thanks to the fact that the states we're interested in, so the ground states of local Hamiltonian, are special, namely that they're much less entangled than a random state from a Hilbert space, which is quantified in this well-known area law of the entanglement entropy. Right, so a matrix product state can reproduce an area law in one dimension, so it's an efficient ansatz for 1D and quasi 1D systems. But you can also use it to simulate systems in 2 dimensions, for example, by putting the MPS on a 2-dimensional lattice with such a snake here. However, because the matrix product state cannot reproduce an area law on 2 dimensions, the involved computational cost here, or the required bond dimension, in the end scales exponentially with the linear system size. So it only scales in L and not in L squared, and only with this length here. And so for this reason, what people do in practice is then do simulations on long cylinders where this length here is small, just up to a certain width. And for the 2D Hubbard model, this means up to roughly a width of 6. Right, so but with this approach, so many groups really successfully extract 2D physics from this approach. Now, a way to overcome this exponential scaling in this end is then to use a 2-dimensional tensor network, and the most natural generalization is then a PEPS, or project entangled pair state, also called the tensor product state, now where we have, again, one tensor per lattice side, but now each tensor is connected to its nearest neighbor by a bond. And now there exists also a version for infinite lattices called an iPEPS, so with which you can really directly represent a 2D wave function in the thermodynamic limit. Okay, so if your state is translation invariant, you can simply parameterize it by one tensor A here, which is repeated on your lattice. But since we're working in the thermodynamic limit, translation symmetries can also be spontaneously broken. So for example, to represent the nil state, we would use an ansatz with 2 different tensors, A and B, which are repeated on the lattice. or more generally, what we use is a certain unit cell or supercell of tensors, which is repeated, right? So here would be an example of a 4 times 2 unit cell. Now, by using different unit cells, we can also target different types of low energy states, which are realized in these unit cells. So in the end, so it's also a way then to find the competing low energy states using this approach. And then in the end of the day, what we then need to do is to systematically compare the variational energies to really see which of these unit cells give the lowest variational energy. Okay, so I will not really go into the details here how we find the optimal parameters in these tensors. So most of the the data I'm going to show you was mostly obtained using an imaginary time evolution. And then you also need an approach to contract the 2D tensor network, which here we use the corner transfer matrix method, but I will not really go into the details of the algorithms. Maybe just one remark here is that if we want to simulate fermionic systems, what we need to do is to include the fermionic statistics in our ansatz. So we have to make sure that we include fermionic anti-commutation rules. Now, this has been worked out by several groups already more than 10 years ago. So I will not go into the details here, but kind of the important message in the end is that this can be done with the same leading computational cost as in non-fermionic calculations. So in other words, taking into account these minus signs here comes really with a sub-leading computational cost. Okay, so let me show you now the iPEPS results for the 2D Hubbard model. So these competing states that we obtain by using different unit cell sizes. So if you use a unit cell just with 2 tensors A and B, we reproduce the uniform D-wave superconducting state, so with coexisting antiferromagnetic order. So what you see here, so these green disks here scale with the local hole density. So you see here it's uniform, and then the arrows show you the antiferromagnetic order. And then finally, these bonds here scale with the local singlet pairing amplitude on the bonds, right? So with different signs in X and Y directions, which is what we expect for a D-wave pairing. Now we can then obtain stripe states by taking a larger unit cell. So here would be an example of a period 5 stripe obtained in a 5 times 2 unit cell. Now you can clearly see that now the hole density is modulated here in X direction. And there's also this typical pi phase shift in the antiferromagnetic order, right? So we have up here, down here, up here, and then here essentially vanishing spin, and then again down here, right? And this is energetically favored because then the hole can fluctuate around this domain wall here without frustrating the antiferromagnetic order. And what you can also see here is that this stripe here actually coexists with superconductivity. Here's another example of a period 8 stripe. So what's special about the period 8 stripe is that it has exactly 1 hole per unit length. So exactly filling of 1 hole per unit length. And in this case, we found that superconductivity is entirely suppressed. There's other low energy states like this diagonal stripe as shown here. Okay, so in the end, what we need to do is to systematically compare the variational energies of all these competing states to find out which of those is really the true ground state. Now, before coming to that, let me show you some other previous benchmarks to get a bit of an idea what the main challenge is here. So first here, I show you a benchmark at half filling. So at half filling, there's no sign problem, so we can directly compare with quantum Monte Carlo. So that's the energy beside as a function of 1 over the mod dimension. So you can see here how the variational energy improves as we increase the bond dimension. And then down here, this is data from quantum Monte Carlo for different system sizes. And the dashed line is the quantum Monte Carlo result extrapolated to the thermodynamic limit. So you can see in the end here, we are similarly close to the thermodynamic limit as the last Monte Carlo point here, right? And we obtain a high accuracy even without extrapolating here. Now, things are more challenging once we go to the doped case. So this is an earlier benchmark for U over T equals 10 at this doping here. Also here compared to another variational calculation based on the variational Monte Carlo combined with fixed node and 2 Lanczos steps. And you see here, as we increase the bond dimension, we can really then also get lower variational energies than in these projected fermionic wave functions. But now you see here one of the main challenges, namely these two states, the uniform and stripe state, are really strongly competing. And as we increase the bond dimension, things don't seem to get better here, but they're actually even more strongly competing. And that's already something which we already observed earlier in the TJ model, right, which is the effective model of the 2D Hubbard model. So that was worked together with Matthias Treuer and Maurice Rice. So the TJ model, you obtain it from the Hubbard model using second order perturbation theory and T over U. And then, so you neglect doubly occupied sites, but then the electrons, the spins are then interacting via a Heisenberg interaction. So in the end, what you see here is very similar to the Hubbard case, namely you have the two competing states, uniform and stripe states, which are very close at large bond dimensions, right? And then the question in the end is really, how can we extrapolate these energies to the exact infinite D limit as accurate as possible to really find out which of those competing states is the true ground state. Now, the problem is often if you do this as a function of the bond dimension, that results are not necessarily very accurate. So let me just show you here one example to illustrate this. So that's for an exactly solvable model of non-interacting spinful fermions. So the details don't matter, but in the end, the exact energy is shown in green here. So this green line. And this is the iPEPS data plotted as a function of 1 over the bond dimension. And you see here, so the last point here is it's a variational value, so it's above the true ground state energy. And then often if you take a linear extrapolation of the 1 over D data, you get something which is lower than the true ground state energy, because in the end of the day, we expect a faster convergence than in 1 over D. You see this is correct, so the exact energy lies in between this interval, in this interval here, but in the end the error bar is very large, right? So it's not very satisfactory. But one way to improve this is, instead of plotting this as a function of 1 over D, we can also plot it as a function of a truncation error, right? So this W here, so that's the same data, but plotted as a function of the truncation error. So that's a quantity which is often used also in DMRG calculations. And here we have used and defined it in the context of the imaginary time evolution algorithm. But in the end, it's also a quantity that goes to 0 in the exact case. And here we find that if we use this data here and extrapolate, we can really get the extrapolation more accurately than in the 1 over D case. Okay, so let's use this technique now to compare the energies of these competing states. So here I show you an example, a comparison of the period 5 stripe with the diagonal stripe. And then, so if we take the extrapolation in the end from this, we conclude that the period 5 stripe is lower than the diagonal. Okay, now we can do the same comparison between the uniform D wave state and the stripe state. And if we extrapolate here, we clearly find that the stripe state is actually lower than the uniform state, right? Which in the end is then the answer to this question we had in the beginning, which of the two is really lower. But now we can move on and then also try to find the preferred stripe period. So which stripe period gives the lowest energy? Now this is more tricky to do. So all the extrapolations give energies which are close together, at least for between period 5 and period 8. There's a slight tendency for period 8 stripes being the lowest in energy, but they're really pretty close. Okay, so let me now also show you the comparison with the other approaches used by my collaborators. And before showing you the data, here's just like a one slide summary of these approaches with their main advantages and disadvantages. I will not really go into the details, but just very quickly. So in DMRG, right, so you can get very accurate results for cylinders up to a certain width. And for the 2D Hubbard model, that was up to width 6. But in the end, you have a finite size error due to this finite width. Then iPEPS, as we have heard, so there's no finite size effects, but in the end, you have to rely on an extrapolation to the infinite D limit. And then another approach is DMT, density matrix embedding theory, where the idea is to map the lattice model onto a cluster impurity problem, which is then solved in a self-consistent way. So there's essentially no finite size effects here, but you have a systematic error due to the finite cluster size, which is used in DMET. And then finally, auxiliary field quantum Monte Carlo. So this is exact at half filling, but if you go away from half filling, there's a sign problem. And one way to overcome it is to use the so-called constrained path approximation, which relies on a good choice of trial wave function for the nodal structure of your wave function. So in the end, there's a remaining systematic error coming from this choice of this trial state. Right, so in the end, you see that all these approaches have their own shortcomings. So in the end, it's not clear a priori how they're going to compare. So let me show you the comparison here. So let's first focus on this plot here. So here I show you the comparison between the uniform state and the stripe state. And here you see that DMET consistently predicts that the uniform state is about 0.01 T above the stripe state. So that's consistent with iPEPS. And then here you see the energy difference with respect to the lowest energy state for different stripe periods. And then you see that all approaches consistently predict a very strong competition between period 5 and period 8 stripes, with maybe a slight tendency for that period 8 stripes are favored here. Okay, then we can also compare the actual energies of the period 8 stripe, and in the end they all lie pretty close in a narrow energy window here, which in the end is quite remarkable given the fact that all these methods come with their own systematic errors, right? So the error bar here in the end is not a statistical error bar, so we don't expect that results lie within the error bar. So because of these remaining systematic errors. But in the end, that's really quite a close agreement also compared to what we had like 5 or 10 years ago when you would compare different approaches. Then we can also compare the different order parameters of the stripes. And now you can see on the quantitative level, you can clearly see differences. So typically the stripe order from auxiliary field quantum Monte Carlo is weaker than found in DMET, for example. But then on the qualitative level, all these approaches reproduce similar features, like the pi phase shift in the antiferromagnetic order, or for example, the absence of superconductivity in these results here for this stripe. Now, let me make some more comments. So a nice thing is actually that in the meantime, the stripe ground state also got supported from variational Monte Carlo. And so for many years, there was always this discrepancy between variational Monte Carlo and tensor network calculations, because VMC would usually predict the uniform D-wave state. But then people have improved these calculations by including the stripe order, the spin stripe order, also in the mean field Hamiltonian, so to create the projected fermionic wave function, so that in the end, they also found then the stripe state as being the true ground state. So that was in the group of Masatoshi Imada and also work in the group of Federico Becca. And then, as we heard in Steve's talk 4 weeks ago, there has also been a work on a more systematic study on the superconductivity in this case. And even when pushing things further, there really seems to be an absence of superconductivity here in the plane 2D Hubbard model. Okay, so in the end, I mean, one of the issues, let's say, with this data is that the typical stripe period that is observed in experiments is not period 8, but period 4. And the period 4 stripe here is now clearly higher in energy. But of course, it might well be that once we move to a more realistic model of the Hubbard model, more realistic model of the cuprates, that these energies might shift in the end, so that period 4 stripe could get favored. And to get more insights into this, what we did was to look at an extended 2D Hubbard model, so including a next nearest neighbor hopping term, which is known to be present in more accurate effective models of the cuprates. So I show you here data which was obtained by Boris Bonsun and Sang-Woo Chu from our group. So that's the phase diagram as a function of T prime over T. For here for U over T equals 10, 1/8 doping, and here for a fixed bond dimension of 12. And what you can nicely see here is that as we increase the strength of the negative T prime, you see that there's a shift from longer stripe periods to shorter stripe periods with a large extended region of stable period 4 stripes. And this includes also values which have been predicted as realistic values for the cuprates. So let me mention that a similar shift in stripe period has also been found in variational Monte Carlo simulations and also in DMRG simulations on width 4 cylinders. An interesting observation here is actually that the competition at finite t prime, so in this region here, is actually weaker than for t prime equals 0. So from that viewpoint, the extended 2D Hubbard model in the end is actually easier to study than the plain 2D Hubbard model, where all these states are much more closely competing. Now let me give you some, try to give you some intuition why we get this shift in the stripe period. And for this, let's compare the energetics of a long period stripe with a shorter period stripe. So here period 7 versus period 4. And let's have a look at the different energy contributions. Right, so what's nice about the period 7 stripes or the long period stripe from an energetics point of view is that it contains these large extended antiferromagnetic regions here with low doping. And that's in the end good then to minimize the effective Heisenberg interaction, right? So if you think in terms of an effective TJ model, the J term in the TJ model will give a low energy here in this region. So the period 4 stripe is worse in this respect because it does not have these large extended antiferromagnetic regions. So the whole doping here is also higher. But what is better for the period 4 stripe is that it has a higher density of these domain walls here of the holes, which is good to minimize the kinetic energy of the holes, which can nicely fluctuate here on the boundary, right? So each stripe has its own advantages and disadvantages from an energy point of view. So a priori, it's not clear which of the two is going to win. So let's have a look at the actual numbers. So here first for t prime equals to 0. So here I show you the different energy contributions in these bar diagrams. And the values have always been shifted by the number indicated on top here. So here I show you a comparison between period 7 and period 4 stripes, so the blue one, of the matrix elements which are relevant for the antiferromagnetic superexchange. So matrix elements between singly occupied sites and then a doubly occupied site with a hole. And then as we argued before, we clearly see here that this is much lower in energy for the period 7 stripe, thanks to these large antiferromagnetic regions compared to the period 4 stripe. Now this comes at the cost of a slightly higher energy of the U term, because the density of doubly occupied sites here is larger in the period 7 stripe. And now these are the remaining kinetic contributions. So here, these are mostly the exchange of a hole with a neighboring spin. And as we argued before, you can see here that this energy is lower in the period 4 stripe. Okay, but in the end, here for t prime equals 0, it's this term here, which is more dominant, such that in the end, the period 7 stripe wins here. And now, when we go now to finite t prime, the finite t prime will induce a frustrating antiferromagnetic interaction along the diagonal, such that these large antiferromagnetic regions are no longer so favored anymore, right? So the difference here becomes smaller, and here on the diagonal, so these are the diagonal antiferromagnetic contributions, here you really pay a penalty. And then the other kinetic contributions, you can see that they get more dominant, and in the end of the day, that's why then the period 4 stripe wins over the period 7 stripe in this case, right? So in the end, you see it's a delicate balance of and competition between different energy contributions. So a priori, it's not clear which one is going to win, but at least we can get some intuition why things shift in this direction. So by the way, whenever there's a question, just please interrupt me and let me know. Right, so I don't see the chat. If there's questions in the chat, this I don't see. Okay, so we have also studied the extent of this period 4 phase as a function of bond dimension. So here you see the phase boundary between period 5 and period 4 stripe as a function of 1 over d. And that's the phase boundary between period 4 and period 3. And you see here, even if we go to the infinite d limit, we still expect a really large extended region here. And then here, I show you the stripe order parameters of the period 4 stripe. So that's the maximal local magnetic moment of the stripe, which clearly remains finite in infinite d limit. And this is the amplitude of the whole modulation, which is small, but which also seems to remain finite in infinite d limit, which shows that both spin and charge stripe orders are stable here. Now, one result we found here, which came a bit as a surprise, is that at 1/8 doping, the superconductivity in the period 4 stripe is suppressed. And that's in contrast to the period 5 to 7 stripes, where we find coexisting D-wave superconductivity. Now, to get more insights into this, we have computed the pairing correlations over an extended range in the period 4 stripe. So here for this doping range here. But let me stress here that this doesn't mean that the period 4 stripe is necessarily the ground state over this entire range. So we did not check which is the ground state, but we do this here to get a better understanding of how the pairing changes as a function of doping of the stripe. Okay, what we found here is clearly the appearance of two different regimes. So if we go to large doping, then there is indeed coexisting D-wave order in the period 4 stripe. So as shown in this picture here, and also if you extrapolate to the infinite D limit. However, this D-wave order is vanishing at small doping. And at small doping, we rather find that the dominant pairing correlations are not in the singlet, but in the triplet channel, right? So as shown here in this picture. However, this P-wave pairing is strongly suppressed with increasing D and seems to vanish in the infinite D limit, right? So that this picture in the end here only reflects the short range pairing correlations in the state, and that in the end of the day, there's no superconductivity here coexisting with the stripe. So what we also observed here is that the energies in the Y direction are lower than the energies in the X direction. So this picture here is then somewhat reminiscent of doped chains, finite with a finite doping, where it's also known that a pairing instability can be in the triplet channel with power law decaying correlations. So in the end, the way things decay here are in the end would be compatible with such power law decaying correlations. Now let me also mention that we found actually evidence of these two regimes already earlier in the calculations of the TJ model. So where we looked at the nematic TJ model, so when you take different coupling strengths in X and Y direction, so here the couplings in Y direction are stronger than in the X direction. And what you find here is that then that the orientation of the stripe actually depends on the doping, right? For small doping, the stripe orients in the Y direction because the Y direction is lower in energy, so it orients itself with the kind of a stronger coupling direction. But as you go to larger doping, there is a transition where the orientation of the stripe changes. But back then, we did not look into the detail of the pairing properties, so we did not find this behavior here. So to summarize, so what we found here is that the pairing in the period 4, the superconductivity at 1/8 doping is really entirely suppressed here. And one can find very similar results also for the other stripes. So also the period 5 stripe shows a very similar behavior, but where this dome here is just shifted to smaller dopings, right? So in the end, we can define, a unit length filling of a stripe, and then we find a very similar transition value between period 4 and period 5 stripe. Namely, if we go beyond a linear filling of 0.57, so that's slightly larger than a half fill stripe, that we get into the D-wave regime, but there's no superconductivity at smaller doping. Okay, so let me summarize this part of my talk. So I've shown you that the doped 2D Hubbard model exhibits many competing low energy states, and that in the end we were able to show that the stripe state has really lower energy than the uniform D-wave state at 1/8 doping. Without the T prime, it's the period 8 stripe, which is lowest in energy, but other periods really strongly competing. And as we switch on a realistic T prime, we find a shift in the stripe period to period 4, which is also the typical period observed in experiments on the cuprates. Okay, but this period 4 is not coexisting with superconductivity, but superconductivity is entirely suppressed. Okay, so this is in the end, not the end of the story, but rather the beginning, right? So in the end, what we are working on right now is to extend these calculations to more realistic models of the cuprate. So considering multi-band Hubbard models and also models with long-range interactions, which in the end are actually not really much harder to do with iPEPS than the one-band case, right? You can just use different tensors for the copper and oxygen sites and then include interactions, for example, up to nearest interactions. Let me mention here that there has been an interesting study already based on the variational Monte Carlo in the group of Masatoshi Imada, where they looked at the effect of the long-range Coulomb interaction, and they found that this shifts, if you include the long-range Coulomb interaction, that in the end, the uniform state gets favored over the stripe state. So it will be interesting to try to see if we can reproduce this also with iPEPS. So in the end, I think doing a systematic study here will really help to get a better understanding of all these competing phases in the cuprates and then hopefully get new insights into the nature of high TC superconductivity. Okay, so with this, I'm done with this part of my talk. So are there questions up to here maybe?
I would have a question regarding longer range interactions. So I think in iPEPS you tend to just sum of all terms in the Hamiltonian, right? Explicitly. And so is that a difficult accounting problem to actually go to longer range interactions?
I mean, there's different strategies one can follow, right? So one could try to encode a long range interactions in some PEPO, for example, or one can also use tricks to sum up Hamiltonian terms at longer distances. So in the end, it's similar to computing, 2-point correlation functions over longer distances in arbitrary directions and introduce this in the optimization of the tensor. So there's different strategies that one can use here, but in principle, I mean, at some point, one definitely does a cutoff or takes into account the even long-range interactions in some effective way, but at least it should be possible to systematically increase the interaction range and then see what this does to the competition of these states. Yeah, thanks for the question.
Maybe I have one question. Many of the unit cells that you use are very anisotropic. If you, instead of using 2 times 5, you use like 6 times 5, would you get exactly the same states, or is it?
I mean, sometimes you see, especially at low bond dimensions, that you might get also some small modulation maybe in the y direction. But in the end of the day, here we found that this does not really lead to a lower energy, and that this modulation would go away at larger bond dimension. So you would find also low energy competing states, which could become modulated also in the other direction. But as we go to larger bond dimension, this does not seem to be relevant here. So there's also these predictions of checkerboard states, so which then really are the same as stripes, but then rotation symmetric, and that's also something we have played around with, but in the end, have not found that this is relevant here.
I see. Thank you.
Thanks.
Did you ever compare these competing states? Like if you calculate their overlap, are they somehow very similar states or very different states still? I'm wondering.
So no, we did not. We have never tried to compute the overlap.
Yeah, because they're like, they have different unit cells, so they seem very different, but of course they could be very similar.
Yes. I mean, one of the question was if, for example, in the uniform states, there's still underlying stripe correlations which are not visible. So I mean, not a static order, but you would see it in the pair correlation. But we did not see that, at least not so far. So yeah, in the end, it seems to be yeah, there seem to be really different states.
Okay, thanks.
Thanks. Yeah. Okay, so I can move on, and then if I mean, you can still ask more questions then at the end of the talk. But let me now go to this topic here. So we also looked at generalizations of the standard SU2 Hubbard model to several species of fermions. So instead of just having 2 species with spin up and spin down, you can also look at the model where you have now n species or n colors of fermions. So we have exactly the same Hamiltonian as before, but where the sum now goes over all these different colors. And these SUN Hubbard models have attracted increasing interest, mostly also thanks to proposals to realize them in quantum simulators based on alkaline earth atoms in optical lattices. So the idea is that you can, for example, take strontium-87 and then exploit different nuclear spin states and then reach up to 10 different colors here, right? So you can identify different nuclear spin states with different colors. And it turns out that the interactions are independent of the nuclear spin, such that this gives then rise to this large SUN symmetry. Now, if you take the model in the strong coupling limit and that integer filling, then these models are also effectively described by a Heisenberg model, as in the SU2 case. So you can just write them with the permutation operator Pij, which exchanges 2 colors on neighboring sides. And all these models in the end are very challenging to study because they typically suffer from the negative sign problem, except in special cases. Now, iPEPS in the past has already been useful in determining the ground states of various SUN Heisenberg models. So it really turns out if you take these models for different values of n and different types of lattices, that there's really a very rich variety of different ground states. So ranging from, you know, different states with different color orders, or generalizations of valence bond crystals, or here in the SU4 case on the honeycomb lattice, we found an algebraic quantum spin liquid. So in the end, so much has been done on the SUN Heisenberg case. And what I also wanted to mention is that here we also got actually support from other methods from my collaborators, so also variational Monte Carlo, linear flavor wave theory, and exact analyzation, which supported all these states here. Okay, but recently we thought about why not trying to go to the SUN Hubbard case, which of course is considerably more challenging. So because you have an enlarged local dimension, right, which grows as 2 to the power of n. And then we also expect that as we go to weaker interactions, that the states will become more entangled. But so we gave it a try for the SU3 honeycomb Hubbard model. So where we already had some previous results on the Heisenberg case, right? So the first goal was to try to reproduce these Heisenberg results. Okay, so let me just show you first the results for the SU3 Heisenberg case. So what has been found actually already in early works using tensor networks is this placket state here. So where you get predominantly formation of SU3 singlets around these hexagons here. So that's a state which preserves the SU3 symmetry. And another proposal was this state here predicted from linear flavor wave theory. So which is a state with a color order, which is at the same time also dimerized and has this kind of larger unit cell here. So here I show you the iPEPS results for the energies of these 2 competing states. And you can see as we push these to large bond dimensions, we clearly find that this placket state is the lowest in energy. Okay, and then so we now try to reproduce results with the in the SUN Hubbard case, so going to a large U over T limit, so to the Heisenberg limit. So by the way, these are all results obtained by my postdoc, Sang-Woo Chung. And you see here, we really obtain consistent results here. So here's the data as a function of truncation error, where we went up to bond dimensions of 27. right? So in the end, here we exploited 3 independent U1 symmetries, so you can really go to large bond dimensions here, and really found results which are consistent with the Heisenberg case, right? So that this placket state here is the lowest. But now we can also go away from this Heisenberg limit and study the effect of decreasing U over T, right? So this is at 1/3 filling, so it's 1 particle per side. And then we observed actually that these 2 states remain the 2 competing states also at smaller values of U over T, but the energies start to shift. So at U over T9, it's still the placket state, which is lower, but as you go to lower and lower energy, at U over T7, the energies become essentially equal, and then at some point it's actually the dimerized state, which is lower in energy, right? So the 2 states in the end are separated by a first order phase transition, so where all the order parameters exhibit a jump at this value here. We then also went to even lower values of U over T. Now this gets more and more challenging, because as you approach the non-interacting limit, the states get more and more entangled. So here we determined the end of this dimer color state by looking at the vanishing of the order parameters. So and that this we observed around the value of 4.5. And consistently also that for values below 4.5, you also see that the charge gap actually vanishes, as you can see here in the density as a function of the chemical potential. Okay, so that's kind of the summarizing phase diagram with these 2 states here as a function of U over T. Right, so in the end, this was somehow a test case to see if we can do SUN Hubbard models. And I think, as in the SUN Heisenberg case, I think we can expect quite a rich physics in these models, and kind of interesting new states of matter that might also appear as you go to change the value of U over T. And in the end, these predictions might then also serve for future, as a predictions for future quantum simulators with alkaline earth atoms. So they are challenging, but I think they have become within reach also of iPEPS simulations. Okay, so now I will use the remaining time to also tell you about some of the methodological developments beyond ground states. So the first thing is simulations at finite temperature. And there have been quite some methodological developments over the past 10 years. I mean, of course, also many developments based on matrix product states, but then also here in 2 dimensions with PEPS. Especially also quite a few works by Piotr Czarnik and Jacek Czarmaga and co-workers. And then also a recent work by Jens Eisert, Roman Orus, also Matteo Rizzi, and Kshetri Mayum. And recently we also had a paper on this, so that was together with Piotr and Jacek. So the basic idea here is, in the end, right, we know how to use a tensor network to represent a wave function. So that's a PEPS here. But in the end, we can also use a PEPS or a PEPO to represent a thermal density operator. So here at a certain beta, right? So beta, the inverse temperature. So that's one possibility. One can also use this to represent the thermal density matrix at half the target beta, and then obtain the density operator at beta by combining this together with its complex conjugate, so taking a bilayer. And this has the advantage then that the representation is Hermitian by construction. Right? So that was the approach we used here in this recent work. And then you can obtain the state at a target temperature or target beta by performing an imaginary time evolution. And this in the end is really very similar to standard imaginary time evolution for ground states, just that your starting point, you start from infinite temperature, where your density matrix is just an identity. So, right, so I show you here just things in 1 dimension for simplicity. So that's your initial state. And then you can evolve this in imaginary time by using the standard Trotter-Suzuki decomposition, right? So we decompose this into small time steps. And in the end of the day, what we need to do is to apply, 2-body gates onto this, onto our state to imaginary time evolve it. And then, as in the techniques for ground states, in the 2D case, there's different ways how we can truncate the evolved state using this simple or full update method. So that's more for the experts. But in the end, we can really just recycle all these techniques that were developed for ground states. Right. So in the end, you see also for the contraction, things can be recycled, right? So imagine if you want to compute the norm. So in the end, imagine you take the trace. So you can also combine, you know, the two legs, so the blue and the green one into one. And in the end, the structure you obtain here is the same as the one of a wave function, right? So bilayer wave function. So we can just recycle algorithms like the corner transfer matrix method to contract these two-dimensional tensor networks in the same way as for wave functions. And of course, another way to look at things is to see the ansatz as a purification of your thermal density matrix, right? Where the green legs are the physical sites and the blue legs are the ancillar sites, and then you can retrieve the thermal density operator by tracing over all the ancillas, right? So here in this, this is completely equivalent. Okay, and the message here in the end is that in the end, if you have a code for ground state calculations, you just need to change a few lines in the end, and you can use this then also to perform finite temperature simulations. Now let me just show you here one benchmark, an application to the Shastry-Sutherland model. So that's a spin 1/2 system on this particular lattice here, and that's an effective model of strontium copper borate. And here I show you data for the specific heat. Now for this coupling ratio here, the sign problem in quantum Monte Carlo is weak, so we can directly compare with quantum Monte Carlo, and you see we get a nice agreement here. If you increase the coupling ratio, then the sign problem gets severe. So you can see here how the error bar explodes in an exponential way as you go to low temperatures in quantum Monte Carlo. Whereas with iPEPS, we can really get this low temperature behavior here in a controlled way. And then in the end here, I show you a comparison with the actual experiments on the material, where we really obtain a very nice agreement of the low temperature specific heat peak. Now things start to deviate here at high temperatures, but this is because spin phonon coupling terms start to become irrelevant here, which are not included in the model. Okay, so in the end, it looks promising that we can use this approach really for problems, to access problems at finite temperature, which are out of reach by quantum Monte Carlo. And of course, the hope is now that we can apply this also for the 2D Hubbard model to study finite temperature properties there. So that's ongoing work, let's say. And then another direction I want to very briefly mention is the computation of excitations using an iPEPS excitation ansatz. So this was all developed in full detail in the Frank Verstraeten's group. So also together with Jutta Hegemann and Laurens van der Straten and other people. And so the main idea is that you start from representation of the ground state, and then you can create an excitation ansatz in the following way by modifying one of those tensors. So you take the ground state tensor and modify here one tensor, putting new tensor B at position X, and then you take a momentum superposition of this ansatz here, which creates you by construction a state with a well-defined momentum. Now, what's really challenging about dealing with this ansatz is that the state itself is not a single iPEPS, but already an infinite sum. So if you want to minimize the energy with respect to this ansatz, you end up here with a triple infinite sum, because there's also infinitely many Hamiltonian terms. And then by exploiting translation invariance, you can bring this down to a double infinite sum, but which is still seems very challenging to do. But indeed, it's possible that one can do this. So this was really first developed by Laurens and other people using these so-called channel environments. So that's one technique. And more recently, we also found a way to do this in the corner transfer matrix framework. So that's work done by my student, Boris Ponsiun. So I will not really go into the details, but in the end, what you need to do is kind of a matter of bookkeeping. So in the CTM method, what you need to do is to keep track of different types of environments. So an environment for the norm of the wave function, an environment containing the summation of all the energy terms, environment containing the summation of all these B tensors for the excitations and then also the mixed terms. And then one can update these environments while doing the CTM in a consistent way, right? So I will not go into the details, but this has also been very nicely worked out by Boris. Okay, so here I show you just one benchmark for the 2D Heisenberg model. So very similar results have also been obtained by Lawrence. So you see the energy of the lowest excitation, and here these are the gapless points. So what you can nicely see here is that for every finite d, we always obtain a finite gap, but we approach the gapless point by systematically increasing the bond dimension d here. And what we did here was actually to extrapolate in an effective correlation length, so making use of so-called finite correlation length scaling here to extrapolate the gap here to 0, which seemed to work quite well here. Okay, so these are benchmarks for the Heisenberg model, but of course the hope is now that we can also apply this as a useful tool to study the physics of the 2D Hubbard model, so for the fermionic case as well. Okay, so with this, I'm coming to the end. So just a brief summary. So I told you how we used iPEPS to try to get new insights into the physics of the 2D Hubbard model. I also showed you an example of a generalization to the SUN case, so which has also become within reach of iPEPS. I really think this is also a promising tool for more realistic multiband Hubbard models, which in the end are not really much harder to do. And this will then allow us hopefully to do a more quantitative study of cuprate materials. I very briefly told you about some new tools that we have. So to do ground states beyond, to do calculations beyond ground states, so at finite temperature, and to compute excitations, which we now try to apply for the 2D Hubbard model. So that's a work in progress. So with this, I would like to acknowledge all my collaborators which were involved in these projects. And in the end, I would like to really thank you for joining tonight, and also thank you for attention.
Thanks a lot, Philippe, for this very interesting and inspiring talk. I guess there's questions. Please ask them.
Maybe for the finite temperature ansatz, would it also be possible to use a purification ansatz, or is it something that would prevent that?
Yeah, it's a good question. You see, as long as we don't do anything funny on the ancilla level, I mean, it's identical, right? I mean, I can write it in this way, and I mean, I can see it as an operator, or I can write it in this way, and it's then the purification, right? So I mean, in this case where the ancilla is kind of has the same dimension, I mean, it's just an extra leg on the tensor. You can see it in both ways, right? And then once you start, but you can do things on the ancillas, right? You could start doing disentangling, as you also did in one of your works, and then it's probably then makes more sense to look at it as a purification.
Right, and then it would also preserve positivity.
That's right. So in the end, exactly. So it's a purification which preserves positivity. Another way to look at it is to see this as half thermal density operator at half the target temperature, and you symmetrize it to get the target beta by multiply to its complex conjugate. So, I mean, it's identical here.
I see.
So I was sort of surprised that you didn't seem to have trouble going to low temperatures. Well, were there any tricks or?
Well, let me, I mean, to be fair, let me say that the Shastri-Sutherland model is, in that respect, kind of a nice model because it's highly non-trivial from the quantum Monte Carlo point of view, but the ground state itself is a product state here in the dimer phase. So the low T behavior here is actually not difficult to obtain, but still, you know, this is relevant for experiments, and it has been extremely difficult to get data here at these temperatures with quantum Monte Carlo. So this is even not standard quantum Monte Carlo, but an improved one where the sign problem, where they managed to weaken the sign problem. So to get these couplings here and even, I mean, up to here, but then to get into the relevant regime, so around 0.62, this is then still, this you can't do with quantum Monte Carlo, but with iPEPS, it was kind of a useful first benchmark to get some interesting results. But of course, if you take a more challenging model, then we expect, of course, getting into troubles as we go to lower and lower temperatures. So what we also are doing now is to look at the problem of strontium copper borate under pressure. So where essentially you go to larger coupling ratios, and at some point there's a phase transition into a plaquette state, so which is no longer a trivial ground state. And of course, that's then much more challenging than what we do here. But of course, it's a very good question. Thanks.
So I have a question about the very first, one of your very first slides, where you showed basically QMC simulations versus PEPS simulations, and the QMC simulations seem to give you lower bounds. Is this something that is a coincidence, or is that something systematic?
Yeah, you see often in finite size data that is often the case that you approach the energy from below, right? So this is the, these are finite system sizes, and then extrapolate to the thermodynamic limit, right? So this here comes from below. I mean, so the dashed line is the extrapolated data in the thermodynamic limit, but the finite system size here comes from below.
Yeah. So, but that means that the combination of iPEPS and Monte Carlo is actually giving you a much better result, because you can sandwich it between the.
Yeah, that's true. Yes, that's true. Here, that's right. I mean, this is the half-filled case, so it's quite well under control with quantum Monte Carlo. But even though, I mean, I think these were still quite heavy calculations, right? Because in these quantum Monte Carlo schemes, I think the cost scales as the cube of system size. So these are not cheap calculations. But indeed, you're right that here, yes, so it's indeed approaching things from both sides. Mm-hmm.
Maybe if nobody else,
I think Andreas raised his hand. Andreas Leuchli.
Yeah, so I feel, so I wanted to ask about the sensitivity of the Hubbard results with respect to optimization methods. So perhaps you mentioned it, but with what kind of updates did you optimize the tensors, and how sensitive are these results to how you calculate the variational energies?
That's yeah. So that's a good question, right? So for the plain Hubbard case, this is using the full update up to high bond dimensions, right? So as mentioned in the plain Hubbard case, the competition was very strong, and we really needed to push also in the optimization to do these very accurate extrapolations to determine which is the true ground state. So then for the T prime case, we had results for small bond dimension with more accurate optimizations like variational optimization and the full updates. But because of the T prime, it's much more difficult to push them to high bond dimensions. So in the end, the large bond dimension results we obtained there was based on the simple update optimization. But it was less of a problem there because the competition in the end was less strong in the T prime, in the finite T prime case. And we already had some understanding of how these states compete and how they compare from the T prime equals 0 case, using the more optimized optimization routines. But in the end, you can say, right, I mean, how to say, so in the end, it was important to really take the best optimization methods for the T prime 0 case to really see if you get a big change there. But in the end, on the qualitative level, in the end, nothing changed. So we used the simple update approach then for the T prime case.
Thank
you. Thanks.
If I might ask something, yeah. Thanks for the nice talk. The part at the end when you, or like a few slides close to the end when you discussed translation invariant excitations, and you had a zoo of different environments. Could you just elaborate a little bit more what's going on there technically? Thank you.
Yes, sure. So this was more like, yeah, just a kind of a glance on what's going on here. So in the end, you see what you have in the end. So this is an infinite sum over the location of the B tensor, where you also need to take into account the correct phase, depending on where the thing is. So this is in the end reflected by this environment here. So what this means, so for example, this tensor here means the edge tensor, which contains the sum of this B tensor here on all the sides living in this edge tensor. Right, so I don't know if you're familiar with the corner transfer matrix. So these environments here, in the end, this contains the upper right infinite corner of the system. This contains a half infinite column of tensors, and so on. Right, so this is kind of the effective environment of the infinite 2D system surrounding some center site in the middle. And so these the empty ones are the environment tensors that we usually have from the corner transfer matrix. So just when you want to compute the norm of the wave function or an expectation value. And the color tensors are the ones which contain a sum of terms, right? So this is then the sum of these B tensors. This is the sum of Hamiltonian terms in this corner. And so in the end, in order to express this here, you need to combine all these possibilities, right? So you have, the B tensors can be here, they can be here, they can be here, and the same holds for the Hamiltonian tensors. So you can systematically write down all the contributions to this expectation value here, right? That you need to compute, for example, the to do the energy minimization. And then the question is then, how can you obtain these environments? And the answer is that, so the way the CTM works is that we let the system grow iteratively. So we do, left absorptions, right absorptions, top and bottom absorptions, and reiterate this over and over such that these environment tensors here contain larger and larger regions from your infinite system. So that's the plain CTM, but now you can also, for example, if you absorb a column onto the left side, you can then also update all these environment tensors, right? So this is schematically shown here. So if you look at this, so this is a new environment tensor containing, the energy and excitation terms. And this new one here comes from the previous step where, both terms are in here plus an empty one. The energy terms can be here, the B can be here, or vice versa, or both can be here, and so on. And this is another term here. So in the end, you systematically add up all relevant terms such that these environments in the end of the day contain all these sums here. So there's no magic about it, but it's a lot. I mean, it's a lot of bookkeeping that you have to go through, and then yeah, that's it. Yeah.
Thanks.
So do you have to do all the bookkeeping while you're optimizing the B tensor?
So I mean, this in the end, this is what you code in your CTM, right? So you have to work out what are all these contributions to this new tensor, and this is in the end. So you need to compute this environment in the end to solve the generalized eigenvalue problem such that you obtain your B tensor, right? So in the end, it's to keep everything fixed. So you keep your ground state tensors fixed, and you only solve the problem for this one single new B tensor that you use to change your ground state.
Right.
So it's yes. So the summation is a challenge, but in the end, it's one can do this. So this is one of the approaches, and then again, as mentioned, there's also the alternative which was developed before with using these channel environments, which also comes with a lot of diagrams. So.
Maybe what Steve was asking is you have to do this CTM, well, all this bookkeeping. So every time you try a new B with whatever method you use to solve the optimization problem for B, every time you try a new B, you have to recompute all these environments.
Mm-hmm. Yes. Yeah. Thanks. Any other question?
So I'm not a connoisseur of this Hubbard model or high TC superconductivity, but as I understand it, it like the special thing is supposed to be that it's a high temperature superconductor. So I was just wondering, is the interesting thing to look at in this Hubbard model really like the ground state physics, or should you have been looking at well, temperature stuff, as you well could have apparently?
Yeah, I mean, both in the end, right? So in the end, right, so with the finite temperature calculations, we could then indeed compute the transition temperature into the superconducting state, or also see what, you know, how these, what sort of competition we actually find between all these states at finite temperature. But then kind of the most starting basic question in the end is what is the underlying ground state as you go to lower and lower temperatures. And now, for example, the fact that if you take the plain Hubbard model and there's no superconductivity for the ground state, you know, tells you that there's probably something missing in the model and that we need to consider more accurate models there. But indeed, so the finite temperature calculations will be definitely also give further insights. Yeah.
Wouldn't the finite temperature calculations even be, like, generally speaking, it's easier once you put the temperature, no?
Yeah, high temperature. But I think if you go
even epsilon, well, okay, if you're near like a finite temperature phase transition, that's no good. But generally speaking, it's supposed to get easier, no?
Yeah, well, at least, yeah, I mean, okay, I mean, there's different ways how you can do finite temperature. And at least in the formulation we used, it's harder to do low temperatures than just plain ground state calculations. I mean, there's ways around that to improve things really as you go to very low temperatures. But yeah, so that's, yeah, it's not so much explored yet. But at least right now, what I've seen so far, my guess will be that at high temperatures, things are fine. At ground states, we have very good ground state methods now, but there's an intermediate temperature regime which is going to be the hardest. That's my feeling.
Okay, thank you.
Thanks.
I think it's probably a good time to thank both the audience and the speaker. Thank you for the people that have been with us already 3 times. There will be another kind of talk soon. We will announce it. So anyway, Philippe, thanks a lot for your talk. Thanks again for all the people attending this. We also appreciate very much that you're asking questions, and we also kind of like to know suggestions if you kind of have wishes or anything. But anyway, it's great to have you all here. It's great to build up this community of tensor network enthusiasts, and we hope that we will be able to do this for a long time. So good night and thanks a lot.